All right, 8th grade. We're going to push on into our next problem, problem 1.2 in our book, Frogs, Fleas, and Painted Cubes. Sorry, this bright sun this morning. It's a relatively quick problem, just looking over the details, remembering what we know about other functions, but also exploring a bit more of quadratic functions. And we'll take a look at that now.
All right, problem 1.2, reading graphs and tables. So in this case, we want to remind ourselves that the relationship between length and area in problem 1.1 is quadratic function. Quadratic functions are characterized by their U-shaped graphs, which are called parabolas, which we talked about in the last video. In problem 1.1, the area depends on or is a function of the length. Recall the relationship in which one variable depends on another is a function. Because the variable area depends on the length, it is called the dependent variable. That means area is the dependent variable. The variable length is independent, and that stands on its own. So these are some of the functions that we've already studied. We've already studied linear functions, inverse variation, and exponential functions. And so in this case, we're looking at these. You can see like the distance covered by a van traveling at a constant speed is going to be linear. The time needed for a van to travel 200 miles is a function of the average speed, which would be inverse variation, because there's that constant of 200 miles. And then exponential function is going to be something that grows at a specific percent per year, or it would be decaying at a certain percent per year, and that's going to be exponential functions. So for today, we're going to learn about the different characteristics of the graphs and functions and equations inside those other functions. We're going to do the same thing here inside these quadratic functions today. All right, so here we go. Part A. The graph shows length and area data for rectangles with a fixed perimeter, just like what we did in problem 1.1. So here we have length, and across the bottom, we have lengths in increments of 5s, it's in meters, and then going up our area in meters squared is going to be counting by 50s. So first things first, we have for part A, 1, describe the shape of the graph and any special features that you see. Well, the shape of the graph shows similar to what we saw yesterday. This is going to be that U shape, or just in case it's upside down U shape. This is a parabola for sure. And so in this case, we want to notice that that is following what we've seen about quadratic functions. The other part here is that we want to notice that we can see that there is a height or a maximum point. That's going to be the key term we want to talk about. The highest point on here is called the maximum point. And you can see that at that maximum point, there's actually this line that kind of could imaginarily comes through that we would have the exact same data on both sides. And that line we're going to call later on called a line of symmetry, which is not going to be any new, or an axis of symmetry. In this case, what we're going to talk about there. If we look at that actual piece, that high peak, the maximum point, we can look and see that it is 20 and 400. So that would be the maximum point, 20 and 400. That's what we would see there in that particular case. All right, so for A1, we have different things we see, a parabola shape. The maximum point is at 20, 400, and the line or axis symmetry is going to be at x equals 20. So you get x equals 20, we get that high point there. That's what we would see. All right, A2. What is the greatest area possible for a rectangle with this perimeter? What are the dimensions of that rectangle? Okay, so if I look at this, the highest possible area that we could get is 400. That's the greatest possible area. 400 meters squared is greatest possible area. Now, if you recall, we were dealing with rectangles from the other previous lesson in 1.1. So then what would be the dimensions of this rectangle? Well, the length is 20. Okay, so think about that. The length is 20. So that means here in this case, I'm going to have a rectangle. This side's going to be 20, and I need to figure out, well, what would be the other parts? But I know the area has got to equal 400 meters squared inside there. So to do that, I would need to do 400 divided by 20. You see it's going to go in 2 times. So it turns out that the overall dimensions would in fact be 20 by 20. That would give me that area of that. So the dimensions are 20 meters by 20 meters. All right, number 3. What is the area of a rectangle whose length is 10 meters? Okay, so if I come here to length, 10 meters, and I'm going to go up to here, what's it going to be? Oh, so 10 meters is going to be 300 meters squared. Okay. What is the area of the rectangle whose length is 30 meters? Let's go out here to 30 meters and go up there. Hey, that's 300 also. So both of those, when a length is 10, it's going to be an area of 300. And when a length is 30, it's also an area of 300. So how are these guys related? That's our next question. How are these rectangles related? So with that side of the length being 10 and the other being 30, that means that the overall area in this case would be 300 meters squared, as we saw from before. If I go up to the 10, it'd be 300, and I go up to the 30, it'd be 300 as well. And you can see that if we actually had this rectangle with those measurements, we would get that particular area in this case. So how are these guys related? Well, they're related because they make the sides of a rectangle that has that area of 300 meters. All right, number 4. What are the dimensions of the rectangle with an area of 175 square meters? Okay, so if I look here, 175 is going to be right here in the middle of these two, between 150 and 200. So if I go right over there, you can see there's a spot. So one of the side lengths is going to be 5, and the other all the way across is going to be 35. And you can see I got 5 and 35. And last one for part A. What is the fixed perimeter for rectangles represented by the graph? Explain how you found the perimeter. Okay, so let's go back and look at the last 3 shapes we came up with. So in this case, we knew that the area was 400 with the side lengths 20. So in this case, if I had 20, 20, 20, 20 all around, then that perimeter would have to be that 20 times 4, which would equal 80. In this case, if I had a 10 and a 30, so 10 plus 30 plus 10 plus 30, that would also equal 80. And this last one here would be 5 plus 35 plus 5 plus 35, and there's 40 and there's 40, so that equals 80. So it turns out that the perimeter of this rectangle, the fixed perimeter, is 80 meters. That's what we would have there. And explain how you found your perimeter. We just did that by looking at those totals. All right, that brings us to part B. So we're going to use this table here to find the questions for these pieces. So again, another rectangle with a fixed perimeter. We have the length and the area. So if there's a 0, it's going to be a 0 area. If it's 1, the area is 11. 2, it's going to be 20. 3, 27, all the way down, and you can see. So number 1, what patterns do you observe in the table? So basically, what we're looking at is, you can see that we've got 0 and 12 down here is going to be 0 for the area. Then I've got 1 is going to be 11, but 11 is 11. 2 and 10 are 20. 3 and 9 are 27. 4 and 8 are 32. 5 and 7 are 35. And 6 is the one in there. So a pattern I see is that that point here, the length of 6, is what we're looking at specifically, is going to get that high point, that top piece there. And so you can see how we have that same kind of folding over pattern. If we graph these, we'd have that same kind of parabola. How compare these patterns to those you observe in the graph? Well, basically, the graph would be the same information as the table data. It's just showing it as a graph. All those plots have been plotted there. So we have that same data there in this case. Okay, number 2. What is the fixed perimeter for the rectangles represented by this table? Okay, so looking at this table, I can see specifically that I know that 1 times something gets 11, and 11 times something gets 11. So that's going to tell me that one of those possible rectangles is going to be a 1 by 11. I don't know if that's 11, but 1 by 11, that's one of the rectangles. And another one, the 2 times something is 20, and 10 times something is 20. So this gives me another one where it's going to be a 2 by 10. So that means that this perimeter is going to be 1 and 11. That's going to be 1, 1, and 11. So that's going to be 1 plus 1 is 2, 11 plus 11 is 22, so that's going to be a 24. Same thing here, it's going to be a 2, oops, that's going to be a 10 and a 2. This is 20, 24, so the fixed perimeter is going to be 24 meters. And we explain that by how we found it out. Okay, B3, what's the greatest possible area for a rectangle with this perimeter? What are the dimensions of that rectangle? Okay, so greatest possible area, it's gonna be 36. So right there, that's the highest it could be. So you can see it goes up there and it comes back down. So that's the highest area. And what are the dimensions of that rectangle? Well, 6 times something gets 36. And knowing my math facts, that would mean that the length would be 6 and the width would be 6. So it would be 36. So for number 3, so area is equal to 36 meters squared, and the dimensions is going to be 6 meters by 6 meters. All right, B4. Estimate the dimensions of a rectangle with a fixed perimeter and an area of 16 square meters. Okay, so 16 is going to be right in here somewhere, right? Right in this area. So 16 is going to fall between those two pieces. So you can see that 16 is 4 away from the 20 and 5 away from here. So it's going to be kind of in the middle, almost in the very middle of this. So an estimate of almost in the middle of here, we could say it'd be reasonable to possibly estimate that it could be 1.5. And then over here, right in the middle of these two, could be like a 10.5. That could be a good estimate there. Number 5. Suppose a rectangle with a perimeter, with the same perimeter, has an area of 35.5 square meters. What are its dimensions? All right, so we're really, really close. We're actually right in the middle of these two guys. So an area would be 35.5. It has to be perfectly in the middle of these two. So perfectly in the middle of these would be 5.5. And an area right with the length right in the middle of the area for 35.5 would be over here would be 6.5. Or actually, yeah, it's right in the middle there. So you can see that we'd have for 5, we'd have a 5.5. And it would be a 6.5.
Okay, part C. Based on questions A and B, describe the change in area as the length increases by 1. Okay, so in this case, the change in area, as we keep increasing length by 1, we have an increase in area, but it gets to a certain point. At a certain point, things kind of stop, and it gets to a high point there because the length ends up being the same as the width, and we have that highest point. But as we continue to increase the length of that, the length by 1, because the width has to decrease to still the same fixed perimeter, we end up having the area decrease and drop back down. And that's the same thing in both of these. And you can see in the graph as well, too. As length increases, we get to a point where the area maxes out, but that length gets longer and longer and longer, and the area comes dropping back down because of the way that the perimeter is fixed, and the width would have to adjust to that there. Now it says here, compare this pattern of change to those for linear and exponential and for inverse variation. Okay, so when it comes to linear, as things increase by 1, we would have a constant rate being added every single time, and we do not have that here at all. Like this is plus 11, plus 9, plus 7, plus 5, plus 3, plus 1, and it starts subtracting that way too. When it comes to exponential functions, remember what we could do for exponential functions, that we actually could look at the information of our dependent variable, and we could divide this one by the previous one and get a growth factor or a decay factor. And we don't have that case here. If I do 20 divided by 11, it's not going to be the same as 27 divided by 20. So we don't have that at all. And then inverse variation, remember, it would be something in the length multiplied has to get that fixed constant number. The relationship between the length and the width, or the x and the y, would have to multiply to get something. In this case, we don't have that at all. These are multiple numbers that are changing all the time.
All right, hope that makes sense. Let's see what the E's work now. For this one, you're just doing numbers 3 through 6.
Number 3, the graph shows the length and area of rectangles with a fixed perimeter. Use the graphs for part A through E. So here we go. We have this length here, the area up here. So again, just like we did, describe the shape. What's the maximum for this fixed perimeter? What are the dimensions? Is there a rectangle with the least possible area? What's the area of the rectangle when the length is 3 centimeters? Describes 2 ways to find those. So same work there. Number 4, use the graph from exercise 3. Make a table of values for the area. And that's too bad. You go in and find those spots there. How is the shape of the graph reflected in the table? How can you use the table to find the maximum area and the dimensions of the rectangle of this area? Number 5, you have information about a petting zoo, and you have this area. It's going to be, they're adding a small rectangular petting zoo for the public there. They have a fixed amount of fencing, so you have the situation of trying to find the right length for each of those. So describe the graph. What's your greatest possible area? And all those questions are there for you. Number 6, same situation here. You've got a lifeguard at a beach. Want to place a rectangular boundary around the swimming area for water basketball. Here are the dimensions. These questions go with that. All right, guys. We'll get the sun. Hang in there. Hopefully it's working out. Hope it's going smoothly, making some sense. Bring your questions to the Google Meets, and we can talk through stuff. I'll post the answers later this week as well. All right. See you around.